Okay, so let us do another example. In this example, discuss the continuity of fx equals to x squared minus 1 over x minus 1. If you remember from college algebra, you see that how do I find the domain of a function? Domain of a function is the x values, okay, where the function is defined, okay, meaning that to find out the domain of the function, we try to avoid these x value that gives you infinity for the function, okay. For example, if there is x in the denominator, you solve that denominator and find out the x value and then say that the domain is all x except that you got from solving the denominator. If there is a root, you try to get the values of x that give you the positive value under the root, right? And you exclude the other values of x that give you the negative under the root. So similarly, since for continuity of a function, we need to have the left limit, right limit, and the functional value equal. But what is the function value? Look at this. The function is a line, the graph is a line, left of 1, the graph is a line, right of 1, the graph is a line, but at 1, there is a hole. Why? Because if you plug in 1 here, you will get 0 over 0. You see that? If you plug in 1, you will get 0 over 0, which is not good, because the graph is, the function is not defined at x equals to 1. But everywhere except 1, the function is defined. You see that it is continuous. At 1, it is not continuous. So you see that, so the function is not continuous. So fx is not continuous at x equals to 1 because f1 does not exist. You see that? Because the f1 does not exist. Okay, now there was a graph, so it was easy to see that there is a hole there, right? If there is no graph, how do I find out where the function is not continuous or where the functional value is not defined? The idea is, if there is a denominator, if there is x in the denominator, you solve that. How do I do that? You do x minus 1 equals to 0. This implies x equals to 1. So the function is not defined at x equals to 1, meaning the function is not continuous at x equals to 1. This is what I find. Okay, so if there is a root under, then you try to find out x values that does not give you the negative values. Okay, so you solve it or write the thing under the root greater than 0. That is the place that the function is continuous. In other places, it is not continuous. Let us look at this exercise, this example. So there is no graph, right? But there is x in the denominator. How do I find out the points or the x values where the function is not continuous? Is you do 64 minus x squared equals to 0, right? Add x squared on both sides. You get x squared equals to 64. Take the root. When you take the root, though, you need to do plus and minus both, right? So you get x equals to plus minus 8. So this function is continuous everywhere except at positive 8 and negative 8. So continuous everywhere except x equals to 8 and negative 8. This is the answer for that. Okay, so this function is not continuous everywhere. It is continuous everywhere except negative 8 and positive 8. This function is also continuous everywhere except x equals to 1. Let us talk about some of the functions that are continuous everywhere. Okay, all the polynomial functions are continuous everywhere, meaning what types of functions are polynomial functions? If there is no x in the denominator, okay, and if all the x's have a positive exponent or 0, positive whole number exponent, positive whole number, okay, or for example x squared plus 5x, x cubed plus x squared plus 9x, all those are polynomial functions. Okay, linear functions, quadratic functions, cubic function, all those are polynomial functions. Some trig functions, for example fx equals to sine x, fx equals to cosine x, are continuous everywhere, but the fx equals to tangent x is not continuous. Okay, because fx equals tangent x is infinity as at pi over 2, negative pi over 2, 3 pi over 2, negative 3 pi over 2, and so on. Okay, so all the trig functions except all the sine functions and cosine functions are continuous everywhere. Okay, next, if a function is not continuous at x equals to a, we call it discontinuous there. Okay, there are two types of discontinuity. One type of discontinuity is removable. We call removable discontinuity, meaning the limit exists but the functional value either may not exist or it is not equal to the limit. Okay, if the limit exists but the functional value is not equal to the limit, because left limit and the right limit equal means the limit exists, right? Limit exists but the functional value is not equal to the limit. That is called removable discontinuity. And non-removable is if the limit does not exist, then we don't worry about the functional value. If the limit does not exist, then it is called non-removable discontinuity. Okay, in case of the removable discontinuity, in this case what we do is, in case of the removable discontinuity, we can make it continuous by redefining the functional value. We'll see an example. This is the example for that. Again, in case of the removable discontinuity, meaning if the limit exists, then we can make the function continuous by redefining the function value. Suppose the function is not continuous, but the limit exists, meaning the function value is not equal to the limit of the function. Okay, in that case, we will be able to redefine the function and then make it continuous. Let us see this example. Let us see the solution. Okay, so we want to check the continuity of this function. So to find out the left limit, limit x tends to 1 minus, which function should I pick? Left to 1. Left to 1 means at 1 the value is 3, the height is 3, but left to 1 everywhere except 1 is this value. The function takes this value, right? So what you do is x square minus 1 over x minus 1. When you plug in the limit though, although it is 1 minus, you plug in 1. You understand that? Because this is just a notation saying that we are going to 1 from left side. So if you plug in 1 directly, you will get 0 over 0. So you don't want to plug in right now. Okay, what you do is limit x tends to 1 minus. So get the factors of the top, x minus 1, x plus 1. These are the two factors over x minus 1. So you got the same factor on the top and bottom. You cancel that out. What is left is x plus 1, right? Limit x tends to 1 minus x plus 1. Although it is 1 minus, you just plug in 1. So you got 2. So the left limit is 2. How about the right limit? Limit x tends to 1 plus x square minus 1 over x minus 1. You do exactly the same thing and then get limit x tends to 1 plus and then x plus 1, right? When you plug in, you just plug in 1, so that is 2. How about f at 1? F at 1 is 3. So the limit exists. Left limit and the right limit are equal. They exist. The limit exists. But the functional value is not equal to the limit. So the fx has removable discontinuity. Removable discontinuity at x equals to 1. But if you want to, you can redefine. You can redefine the function like this. You can redefine fx equals to, if you define x square minus 1 over x minus 1, you cannot change the piece that has x. Okay, if x not equals to 1 and then 2 if x equals to 1. If you define like this, you will have left limit and right limit equal and the function will be continuous. So for the removable discontinuity, you can remove the functional value and replace by a number that is equal to the limit. You see that? And then you can make it continuous. But when you have a removable discontinuity, you can replace the functional value only. You cannot change this function to make it continuous. Don't change this function that has x. Only change a number only. If there is a separate number there, then you can change and make it like this one doesn't have x, right? So you could change this 3 to make 2 and then define it as a continuous function. But if it has like 3x, you will not be able to do that. You cannot change it. You will say it is non-removable discontinuity. You understand that?